Hello everyone, I'm Supriya Kanth. Today I am giving a short presentation on portable H2S gas detection and alert system prototype using highly sensitive nanocrystalline SnO2 thin film. Let us move towards the introduction. H2S belongs to some of the major polluting gases. Others may be SO2, NO2, volatile organic compounds, carbon monoxide, etc. So H2S, the main source is vehicular pollution, coal mines, natural and crude oil manufacturing industry. So H2S can cause breathing difficulties, irritation in eyes, dizziness. It is highly toxic in nature and it is highly flammable. It can cause life-threatening situations in coal mines, in natural gas or crude oil manufacturing industry, and in sewage treatment plant also. So the threshold limiting value set by the environmental governing bodies for H2S is it should be less than 10 ppm in 8 hours. So we need a very compact, portable, handheld, highly sensitive, highly specific for H2S, and it should be reliable. At the same time, it should be cheap. So our sensor is based on the chemi-resistive, sorry for the wrong spelling, chemi-resistive based method. We are using nanocrystalline SnO2. Ours is very compact, portable, wireless electronic alarm unit which uses very less input power, less than 5 volts. It operates at room temperature. It is basically fabricated to monitor H2S leak. Now let us move towards the next slide, which we'll see the basic principle of a chemi-resistive sensor. So basically this is a experimental setup block diagram of a chemi-resistive sensor. So it's a sensing material. Most of the sensing materials are metal oxides, and it has got surface adsorbed species in the form of O- and O2-. So when the target gas molecule interacts with these species, change in some surface phenomena happens, and that surface phenomena reflects the change in electrical parameters, the resistance or current, and it is measured at standard electrometers or potentiostat, galvanostat. So the SnO2 which I'm using is prepared using Langmuir-Blodgett technique. Around 115 to 120 layers of this film has been deposited, and what is the mechanism of SnO2 is basically while preparing SnO2, many of the SNO bonds get broken and it creates the oxygen vacancy. Here we are representing the surface of SnO2 by this line, and this is the whole bulk thing. So the surface, when the atmospheric oxygen interacts with the surface of SnO2, it takes electron, the oxygen is very much electronegative in nature, the ambient oxygen. So it takes electrons from the conduction band of the SnO2 and sits as O- or O2-, and a depletion region or a space charge region is created between the surface bulk interface. So SnO2 being an N-type semiconductor, H2S, when gases, reducing gases such as H2S interacts with the surface of this SnO2, then it gives electron back to the conduction band of the SnO2, and so SnO2 N-type means majority carriers are electrons. Electrons are given back to the conduction band, so conductivity will increase for reducing gas, and for oxidizing gas, the opposite phenomena, that is conductivity, will decrease. So here are the results. We have used different experiments set up for optimizing the parameters. So this is one of the setup. It's a closed chamber, glass chamber, coated with a dark paint. It has got inlet, gas inlet and outlets. So this is our sensor. It is the film has been deposited on quartz substrate, and we are using interdigitated gold electrodes. This sensor has been mounted on the top of this glass chamber, and these are the standard gas canisters. So in terms of resistance versus time plot, I'm showing the response. So these are the points where the gases were, H2S was injected, and from this plot, I have calculated the response using this R final minus R initial upon R initial into 100. And for 4 devices, here I am showing the linearity of the response for 0 to 10 ppm. Some selectivity experiments has also been done. So we found that it is highly selective for H2S. 1 ppm of H2S, NH3, ethanol, NO2, and 1% of hydrogen has been injected, and we found that it is highly selective for H2S. For a real-time monitoring purpose, we have used this small housing setup. It has got holes for gas inlets and outlets. So this was first calibrated using the standard potentiometer or electrometer, and we found that the response time is very fast. It is of around 15 to 20 seconds. The recovery time is also very fast, that is 10 to 15 minutes. And we observed almost the same response that has been observed using the closed glass chamber setup. Now, optimizing those parameters, we have now, like it's a prototype, we have made one electronic alarm unit. So this is a block diagram. This is our sensor. We have used some current to voltage converter sensor circuit. So from that circuit, we get response in terms of change in voltage that is given to the microcontroller, and finally we get the gas concentration in the display. So it's another housing setup. It is made up of polylactic acid. It's a very light material. The weight is around 10 grams, and the overall weight of the unit is around 100 grams. So in our circuit, we are using one reference sensors and one active sensor. Both of the sensors are exposed to same external environment effects. Only thing that the active sensor will only be exposed to the gas, and reference sensors will not be exposed to the gas. So we'll get the difference between V01 and V02. V01 is the output because of the active sensor, and V02 is the output because of the reference sensor, so that we can get a genuine change in the signal because of the gas. So here's the V dash is basically the difference between V01 and V02. And from this circuit, electronics alarm unit, only we have calibrated our sensor. Here I'm showing the voltage versus time plot for up to 20 ppm of H2S. Here the response has been calculated using this V final upon minus V initial upon V initial, and then 100. So from our electronic alarm circuit, we were able to achieve linearity for the concentration from 0 to 40 ppm. The sensor's response for day 1 and day 2 was also almost similar, and almost 4 devices has been for reproducibility. We have tested 4 devices which gave almost the same response using our circuit. And using that electronic alarm circuit, we again experimented the selectivity thing. So it is highly selective for H2S, we can see. So Yeah, some of the commercially available sensors based on the optical principle, they are highly selective, sensitive, but the drawback is they are non-portable. Not all, but almost, but they are highly costly. Second one is based on electrochemical. Mm, they are cheaper, but also they works at ambient temperature, portable, range of the detection is also very good. But the drawback is when the electrolyte dries up or something, so we need to change the whole sensing setup. In our case, it is not that. We need to only change the sensor, which is kept in this housing. We only need to change the sensor. The circuit can be used for another set of sensors also. Now I'd like to conclude that our electronic alarm unit is very much portable, compact, handheld. Its detection range is also very good, 1 to 40 ppm. The sensing material we are using here is nanostructured SnO2 thin film using Langmuir-Blodgett technique. Sensors has been studied for their response, selectivity, reliability, accuracy parameters. It also uses less than 5 volt input supply, very lightweight material it is. And so the overall system is hazard-free, compact, and reliable. Thank you.